The broadcast is now starting. All attendees are in listen-only mode.
Good morning, afternoon, and evening, everyone. My name is Rob Meyer. I'll be your host today with GridGain. We're going to begin in just a moment, but first I just want to conduct a few tidbits of housekeeping. First, if you could raise your hand using the hand icon located in the GoToMeeting control panel, the GoToWebinar control panel, let me know if you can hear me. You can just click the little hand icon there. Perfect. So looks like we are good to go. During this webinar, you're going to be on mute, but if you have any questions during the discussion, I will be watching while Akmal is presenting. So feel free to enter them, and then I'm going to save the hardest ones for last. I always do, so please give me some good ones. It's always fun to try and stump Akmal. Today, we're lucky to have Akmal. I don't know if any of you have heard Akmal Chaudhry present before. He is a technical evangelist for GridGain. He really focuses actually on Apache Ignite and the Ignite community. And he's going to be talking today about machine and deep learning or continuous learning with Apache Ignite. He's going to be showing how it's used. So please keep this as interactive as possible, because hopefully by watching Akmal, you're going to understand as well how it works and how to actually get started with it and start to use it. So with that, let's turn it over to Akmal. Akmal, take it away.
Okay, well, thank you very much, Rob. Very gracious introduction there. And thank you for everyone that has joined. Yes, and indeed, I'll echo the sentiment. So good morning, good afternoon, good evening, wherever you are in the world. Thank you for joining. For me, it's evening time, so it's just gone past 7 p.m. here in London. So I look forward to this webinar and then look forward to dinner afterwards. So I have some motivation to try and finish, and I'll do my best to wrap up early if I can, okay, to give you back some of your time as well. So we've got not that much in terms of actual slide content, and some of this we'll be able to get through fairly quickly. I do have a few small demos to show you and some resources to share as well at the end, where I can show you where you can download things and what additional material that you should be reading if you want to get up to speed on this. So with that, let me just switch into presentation mode here. So I hope you'll be able to see that. Okay, so Apache Ignite, in-memory performance, durability of disk. So we'll discuss this in a bit more detail as we go along, what these actually mean. So the in-memory performance, historically, so the in-memory data grid, where Ignite has come from, but durability of disk, okay, so the ability to save data, persist data beyond the lifetime of the process that created it is one of the sort of newer capabilities that was introduced last year. And that has some importance and significance to the presentation today, and we'll drill down into a little bit more detail on that later. So as Rob was saying, so today's focus is really on what it says, machine learning and deep learning with Apache Ignite. And so my role, as Rob mentioned, is really to focus principally on the open source technology, Apache Ignite, although GridGain very graciously obviously pay my salary and various other benefits that I get from them, but very much so in terms of the focus for me is more on the open source side of things rather than the commercial side of things. But obviously we have additional capabilities on the commercial side, some enterprise features, which would be very useful for larger customers or any customers actually. And those features give additional capability that isn't available in the open source version. We're more than happy to discuss those with you if you are interested. How to contact me? Very easy. It's just first name dot last name at gridgain.com. So akmal.chaudhry@gridgain.com. Be sure you spell my surname correctly. It's from South Asia. There's about 8 or 9 different ways to spell it. Very easy to make a mistake, but feel free to reach out to me if there's anything further that I can assist you with, and I will do my very best. Okay, so as far as the agenda goes then, so a very brief overview of Ignite. I think this is important because it gives some context to some of the components that we'll discuss a little bit later on. And then I term this as data science toolkit, because really it's more than just these machine learning and deep learning capabilities that we're going to talk about. So there's a whole range of components that Ignite provides. Many of these are very well suited to analytics and machine learning and deep learning. It's kind of important to understand these features as well, despite the fact that you may not use them. It's a case of these libraries are available, you can use them, but if you understand some of the context and the background and some of these components, that will give you a sort of a better appreciation of how things actually work in Ignite. So particularly we'll look at the memory-centric storage, okay, which is very important, the compute grid, which really forms the foundation for some of the machine learning and genetic algorithms, which we'll talk about a little bit later on. And I will show a couple of demos as we go through. They're very simple and straightforward. It should be very easy for you to replicate exactly what I've done. And I'll show you exactly where to get the code from as well. Summary, and then time for Q&A at the end. Okay, so this is the big picture. I think, as many Americans would say, it's the kind of 30,000-foot view or 50,000-foot view, the high-level view of what is the Ignite architecture. And if we look at this graphic, then at the heart, we can see this memory-centric storage. So historically, where Ignite has come from as an in-memory data grid that was built by GridGain, I think over 10 years ago now, when the initial work was done, as a company, certainly GridGain has been around for that long. And this was subsequently donated to the Apache Software Foundation. So originally, very much focused around caching and key value capability, which we can see just above there. But increasingly, particularly this last year, a lot of additional capabilities have been added. So SQL, for example, SQL 99 support. This was a goal that was launched last year, and that capability has now been added. So in some respects now, you can treat Ignite as a distributed SQL database if you want to work at that level. Transactions, very important. So, this is far beyond just normal sort of caching that we might want to do. So the ability to move the system from one consistent state to another consistent state, and also be able to integrate with third-party systems, which we can see down in the bottom right there. So things like transactional database systems, such as relational systems, Postgres, MySQL, Oracle, and others. And the nice thing here is that we have some choices. So it can be lock-based transactions where we are ensuring that consistency is maintained. So these kind of ACID capabilities, if you like, atomicity, consistency, isolation, or lock-free, optimistic transactions. In some applications, perhaps we don't need the overhead of locks. Now, these are very, very useful. So just give you a quick example from my own personal experience. So I'm a great fan of these massive open online courses, MOOCs, and I like Coursera, EDX, and others. And I regularly go there to, equip myself with some new skills from time to time. So earlier this year, I happened to be on the website of one of these offerings, and I decided I would like to pay with my credit card. I entered in my credit card details. Unfortunately, it came back and said, there is an error. At the time, I didn't think too much about it. I thought, okay, there's an error. That's fine. The transaction didn't complete. It's not a problem. Sometime later, I check on my credit card bill, and I noticed that actually the bank has billed me. So going back to the merchant, they said, we haven't received the money. The bank has charged me. So unfortunately, I'm kind of left in the middle. So, this type of scenario should not happen. And again, if we envisage the situation where perhaps I want to transfer money to Rob, we need to ensure that the money leaves my account and is credited to his account. We can't have the situation that it disappears from my account and does not appear in his account. That's not allowed, and it shouldn't be allowed. So consistency is very important. And there are certain, vertical markets, industries where this type of thing is a must, okay? And then Ignite supports these level of sort of transaction control. So ensuring that the system moves from one consistent state to another consistent state, these lock-based transactions are very important. And again, the ability to handle things like exceptions, failures, deadlocks, all of these capabilities are available as well. Compute grid, service grid, we won't focus on too much on service. We'll say a little bit about the compute grid later on, and I'll show you why it's important. Streaming, obviously, for many types of applications today where we are receiving things like sensor data, for example, or IoT type data, then the ability to combine that, as they say, we refer to this thing as sort of fast data. We take that, we combine it with perhaps historical data that we've got in these data lakes, warehouses, and then be able to derive some useful information, business insights. I think this is very, very important as well. So again, Ignite doesn't offer its own sort of streaming engine per se. That's not what we're about, but it does provide connectors and adapters to be able to integrate with popular streaming technologies such as Spark and Flink and others, for example. And of course, the last one on the right-hand side there, as we can see, machine learning. So this has been in beta for some time. This capability was offered in 2.4, which was released not so long ago. And then again, there's more sort of features coming along in 2.5. And then there's additional capabilities that are being discussed on the dev list and others. And again, all of these things, it's a community-driven project, so it requires time and effort. Resources, so very much what the community prioritizes, but there are things on the roadmap such as support for TensorFlow, Python and R and these type of environments, which I think are very relevant to data scientists and machine learning specialists. Along the bottom there, so I briefly touched on the third-party persistence already. So for transactional systems, Ignite provides some very good capabilities. So the ability to take data from a relational system, for example, cache that in memory, and offer the ability to work with that data in a transactional manner, and again ensuring that that data, all of that data, are consistent both in cache and in the backend relational system. So changes in either are correctly reflected, and the system maintains its consistency. This is very important. But equally, and there are some blog posts written, my colleague Dennis Magna, for example, has written about this as well, and Rob has written some material on this as well, looking at other technologies that aren't transactional. So things like NoSQL databases, which tend to be the vast majority as are eventually consistent. So there is a kind of different kettle of fish. We have to treat things a little bit differently, more carefully, because there are no guarantees that the database system can provide us. It's about certain sort of things that we know we can do, and perhaps we are content with the fact that not all the data that we see across the system is consistent. The native persistence on the left-hand side, again, very important, particularly if we're dealing with large quantities of data, which seems to be the case today. So despite the fact that memory is cheap, certainly we can store a lot of data and process that data at memory speed, which is one of the significant benefits of Ignite in terms of scale and performance. This is what we're trying to achieve. Nevertheless, the amount of data, the quantity of data that we are working with today, tends to be far larger than we often need to store all of this in memory. But that ability to store that data, page in what we need, and work with the sort of the data that we need, and Ignite manages all of that for us. I think this is a really sort of a strong feature and a strong capability beyond just simply the in-memory data grid and the historical sort of space that Ignite originally came from. So lots of great stuff there that can really help deal with vast quantities of data, give us great performance, work with industry standard tools such as SQL, for example, and the whole range of things that we can do with the data once we've got it. So working, analytics, doing machine learning, all of these capabilities become possible, and that really makes a big difference. Okay, so in terms of the machine learning, then what's the business case? What's the reason for adding machine learning capability? Well, the thing is that historically, then, if we look back in time, how people did this previously with Ignite, and perhaps this is true of other in-memory data grid technologies as well, that unfortunately, it was the case that you had to do an ETL, extract, transform, load. And whilst this may be okay for small quantities of data, unfortunately, because we are dealing with a lot larger amount of data today, it makes this task somewhat unrealistic. Okay, it becomes difficult. So taking that data out, doing some transformations on it, and then loading that data back in again, I think, especially when we're dealing with sort of hundreds of gigabytes up into the terabyte range or beyond, as the case may be, it's not feasible. We want the ability to process that data where it is. So we don't want the overhead of running other technologies and waiting for results to come back. So there is no need to redeploy models in production. Okay, that's one of the key things. The other thing is scale, of course, that data exceed capacity of single server. I've touched upon that several times already. And typically today, it's not just simple solutions that we need to think about. We may be looking for complex answers, complex solutions to problems, and that's entirely possible. With cluster computing and all the benefits that it brings, in-memory sort of processing and all the benefits that brings, there's a lot more that we can do today than we could ever do. And then the last point there, in terms of burden for developers, okay, so what we want to try and do is, again, not just get sort of business benefits in terms of the productivity that we achieve as business people, the decisions that we can make faster, the opportunities and the threats that we can identify, but it makes the lives of the developers much easier as well, because there's less work for them to do. There isn't the need to focus on a lot of these sort of complex issues in terms of how do we get this data out, how do we apply the transformations, and then what do we do with that data subsequently. So the fact that we can work on this data in place and apply various machine learning algorithms, I think really is going to help a lot of businesses going forward. Okay, so let's look at some of these architectural components and see why they are going to be particularly helpful to us. So one of these things is this memory-centric storage, which I've touched upon and discussed a little bit already. So one of the things that, being a Java-based system, obviously there are certain things that affect overall performance. And if you're familiar with Java, things like garbage collection, for example, stop the world garbage collection. And particularly if you're working with large amounts of data, and this is a kind of a showstopper. So with Ignite, what they've done is they've developed its own memory management system to basically reduce some of these problems. So it will take care of these things. It will do things like automatic defragmentation. Memory consumption becomes much more predictable as well. And so the garbage collection issues become far less. Obviously, still some issues there in terms of how Ignite works, but basically they become less of a problem going forward. There's other things as well here which are shown transactional write-ahead log, but we won't discuss those today. But the key point here is, again, in the bottom right there, store superset of data. So perhaps that's not really the correct phrase, but what we're trying to say is that all of the data are stored on disk. Some of that data may be cached, and it depends upon how much data we have. If we have far larger data than we can store in memory, then using this memory-centric storage capability really gives us benefits. And again, as we access certain data, Ignite will take care of that. It will retrieve that data, page out old data for us based on some algorithms, and give us the ability to process the data that's in memory. And again, we get the benefits of memory speed, plus the benefits of working with much larger data sets than we might do otherwise. The compute grid, so this is one of the core components of Ignite that has been around for a very long time, extremely mature, very robust, very capable. And if you're familiar with things like fork join, for example, or MapReduce, this is exactly how it works, okay? So here we can see an example of a compute task coming in from the left-hand side. That task is divided up into a number of jobs, depending upon sort of the cluster resources that we have available. In this case, we've got 2 nodes on the right-hand side, so we're able to break that task down. These are submitted as jobs, so it's a case of divide and conquer. Parallelize the operations. We get the results back, we combine the results, send them back to the client. Now, in this case, we're assuming that these two cluster nodes are of equal capability, and therefore we can do the work in half the time. As you would expect, all of the standard sort of capabilities in terms of cluster computing that you would really want to see, things like load balancing, for example, automatic failover, these capabilities are already provided by Ignite. One other thing I would just mention there, which is on the right-hand side, it says zero deployment. There is a very useful feature that Ignite provides called peer class loading. So it's this ability to really, as you modify the code and you execute some tasks, the servers don't need to be restarted, okay? The code is pushed out for you. Now, that's great in testing environments, okay? You may want that automatic capability because it saves a lot of time. So it's a great productivity feature and can really help in terms of, especially in sort of machine learning space, for example, where you may be iterating, trying out many different models, and this can really boost productivity significantly. In production environments, you may probably want to be a little bit more careful. So, automatic code being pushed out directly to the servers is something that you might want to control. It may have unintended consequences otherwise. And in production environments, especially when you're dealing with large quantities of data, I think that's just sort of, better to be on the side of caution there. Keep this picture in mind, okay? We'll use something very similar in a little while, and you'll see the similarity. It should sort of come through. Okay, so in terms of the machine learning then, so there is dense and sparse algebra support, distributed algorithms, okay? And I'll show you a couple of examples of these very shortly. So k-means, regression, decision trees, and so on. All the benefits that we talked about, things like large-scale parallelization, okay? So the ability to run these algorithms now across the cluster, use the power of the cluster, and that will speed up, the performance significantly. And again, one of the other significant benefits is no ETL. So now we don't need to do this task of having to extract the data out, do the transformations, perhaps using other tools, and then loading the data back in or loading it into other sort of tools if we need to do that. So working on the data in place, I think that provides a significant benefit, really. And for those of you who are working in the machine learning space already, you'll know that the ideas behind machine learning have actually been around for a very long time. Many of the foundation, the math and statistics, those things have been well known for a very long time. I think the problem has always been the ability to run these jobs, these tasks much faster, get insights much faster, and things like cluster computing and technologies such as Ignite really can help significantly in this space. I think the other thing is that I think certainly as far as GridGain is concerned, we have customers out there now who are asking for some of these capabilities. They want to be able to run these machine learning algorithms directly on the data that they have, and therefore it's really driven in part by their demands as well. Now, the level of support as far as the algorithms are concerned, it's not that these are very exotic algorithms or these are sort of very exotic sort of technologies that we deal with. These are very sort of practical, very pragmatic things that will work today. I mean, they are useful for business applications today. And the fact is that these have been, the libraries have been written from the ground up. So this notion of distributed algorithms is very, very important. So the ability to really use the power of the cluster, I think, shines through. I mean, this is very important. Otherwise, there would be no benefit. I mean, you would not be able to get any significant benefit if you could not do this. Okay, so one of the things, the approaches that I touched on briefly a little bit earlier on, I mentioned this notion of sort of key values. Okay, so at its core, when Ignite was originally developed by GridGain, this notion of an in-memory data grid using sort of key value. Then there is this, how do we actually store the data? The key, we apply an algorithm to it. It's data are partitioned across your cluster. It tells you, the hashing algorithm will give you an indication of which particular node in your cluster that data should be stored on. So there is this notion of partitions. Okay, so partitions are atomic. A node may store multiple partitions. What we have is something like this then. So often you'll see in the Ignite literature this mention of a cache. Okay, so the cache consists of multiple partitions. Here we have two examples, and there we've got in partition 1, for example, key 1, value 1, key 2, value 2, and so on. And similarly with partition 2, key 5, value 5, and so on. All right, so cache, think of that as an aggregation, a little bit like a relational table, if you like. And this is cluster-wide. But we need some sort of way to be able to store that data sort of atomically, if you like. And we have this notion of partitions because we can then do things like replication. So let me show you a quick example. Here we've got a simple 4-node cluster. We happen to have 4 partitions here, 0, 1, 2, and 3. And in this particular example, we see that each node is just storing 1 partition. If we happen to lose one of these nodes, you can see now that particular partition, all of that data, it's no longer available. We can't see it. It's gone. However, there is an ability, and this is true for distributed systems, that typically we will create backups, and it really depends on how much data you want to back up. If you've got small quantities of data, then in theory you could back up all of the data on all of the nodes that you have in your cluster. I mean, that's an extreme case. I think it's fairly standard in the distributed environment to have at least 1 backup and perhaps 2 backups. So in this case, we've got our 4-node cluster again. We've got our partitions there again. But in this case, what we've done is we've created a couple of backups. Okay, so we've taken these primary sort of partitions. In the blue, we've created backups, backed up the data on other nodes. And therefore now, if we lose a particular node, in this case, let's take node 2 down. So we notice that partition 1 and partition 0, if we would face the similar situation that we did before, but because we have these some data backed up, there is the ability still to access that across these other 2 nodes. In this case, node 1 and node 4 give us this sort of capability. Okay, now there is a reason why I'm mentioning this, because one of the capabilities that has been introduced is this notion of a partition-based data set, very useful for machine learning. And again, I'll say a little bit more about that very shortly. So it's something that sits between the machine learning algorithm and the actual storage and computation that Ignite manages for you. It's based on MapReduce, okay, which is a well-known approach, very good. If you've worked previously with technologies such as Hadoop, for example, and I talked about this and mentioned this very briefly a little bit earlier on when we were looking at the compute grid. So this ability to take data, reduce the data down, and then perhaps we want to iterate over that and do sort of more work on that data, it's entirely possible. But it gives us some sort of flexibility. It provides the better ability to handle things like failures, for example. So what we have is this notion of partition data. As we saw in the sort of last couple of slides there, that if we've got backup copies, okay, we can recover that data to another node, all right? There is this partition context as well. Now, this is important because in the case when we are running things like machine learning algorithms, a lot of them tend to be very iterative, and they need to have some context in terms of the data that they're working on. So in the event that we lose some part of our cluster, it's going to be very difficult for us to continue processing because the data are gone. We've lost the processing as well. And therefore, if a machine learning job, for example, has been running for 20 minutes or half an hour or an hour or something like that, then that causes a difficulty. We had to restart again. So with this partition-based data set approach, there is a degree of robustness built in as well now. And the way we can kind of see this is a little bit like this. So now we've got a couple of nodes here. We happen to store a partition on each of these. So we've got one on node 1, one on node 2. We've got some partition context, and we have some data as well that we are working on. And we can apply some training, reduce the result set, go back to our client again, and perhaps we need to refine that again. So you see the client may make additional requests back to node 1 again, okay? So this is a sort of an iterative cycle that may go on. The thing is that, as I mentioned, typically for a lot of machine learning algorithms, because it's an iterative approach, using this kind of partition data set gives us some degree of robustness and again, helps in terms of recovery. So in the event that some node has gone down or parts of our cluster have gone down, if we've made sufficient provision, then what it is that this partition context keeps information about the state. Where was it at the time it was processing that data, and we have some level of recovery. So looking at this example, if we backed up all of the data, this partition context, partition data from node 1 onto node 2, then if node 1 goes down, we've got that ability to pick up where we left off from node 2. I mean, that is really it's the real benefit that you get from this, in not having to go back, restart your jobs, but being able to pick up from where you were. Using things like MapReduce at this level, I think, really provides a significant benefit. One other thing you'll notice there as well, that there is a kind of a D star there on Ignite Node 2, and I put down there in the bottom left-hand corner, sort of local ETL. So it's entirely possible that some of the data, for example, may have been stored locally, and it may be able to process locally. So there is no need to retrieve that data from another node upstream. That's entirely possible as well. Okay, there may be situations where you can just do that without having to retrieve data from elsewhere in your cluster. And again, thinking about how distributed systems are designed and how they sort of tend to work, it's all about bringing the processing to the data. We want to minimize data movement as much as possible. And there are other things that Ignite can offer, things like collocated processing, for example, that we store data that kind of makes sense, together with other data. So if we happen to be a car manufacturer, then the actual vehicles that we make, the different types of models, for example, or we have sort of countries and the cities that belong to a particular country. A great example might be from a few years ago. If you think about the hurricane, for example, that hit New York late 2012, suppose we wanted to build some kind of weather alert service by co-locating the people that actually live in the city with the city itself. We know exactly where the data are. If we want to send out some kind of alert message to all the residents of New York, prepare, there's a bad storm coming, it's very easy. We know where that data resides. And again, these ability to recover from failure, this partition-based data set gives us a lot of flexibility in terms of handling the data and being able to cope with these sort of situations where things become unpredictable. Life, in terms of computing, I think it's a case that Murphy's Law, anything that can go wrong will go wrong at the worst possible time. So you try and prepare as best as possible. Oh, oops, one too many slide there. So what about the actual algorithms then, and the what are the sorts of problems that they could be applied to? Well, we'll look at a couple of them very shortly, but generally they fall into a couple of different categories. So classification is a great one, and the example that you might often come across in the literature, things like spam detection, for example, or image recognition, credit scoring, disease identification. See, all of these are very, very relevant and very useful. So if you think about Google, for example, or you happen to be a Gmail user, then you'll know that they do a lot of this spam detection already. So they train a lot of their system based upon the type of spam messages that are generated. And therefore, when email comes in, it's able to make a sort of a good prediction based upon data that's been trained on to identify that. And often you'll see it does a very good job in terms of just sending that message to the spam folder already for you without you having to read it. Image recognition, another great one, that sort of very widespread use of this technology today. but also practical things like credit scoring, for example, disease identification. I think these are very, very useful. Some of the algorithms themselves, then we've got things like nearest neighbor, decision tree classification, neural network, and again, we'll look at a couple of these very shortly. In terms of regression, then, so the description says modeling the relationship between a scalar-dependent variable y and one or more explanatory variables x. Some examples there: supermarket revenue, drug response, stock prices. Another one might be things like house price, based upon some characteristics that you have, floor space, number of rooms, location, size of property. Could they help predict what is the actual price that we may want to sell that property for? And again, in terms of the algorithms, things like linear regression, decision tree regression, nearest neighbor, neural network, and so on. And again, we'll look at those very shortly. Moving on a little bit, so things like clustering, grouping a set of objects in such a way that objects in the same group are more similar to each other than to those in other groups. Very practical sort of applications of things. So from the perspective of things like customer segmentation, grouping shopping items. So one of the algorithms that's supported in Ignite is sort of k-means clustering. Okay, and again, we should have a look at that very shortly. Now, one of the things that is often the case, especially with a lot of machine learning data, is the ability to sort of pre-process that data and look for things like feature extraction. Okay, this can be a time-consuming process, and I think anything that can help the data scientist or the machine learning specialist achieve this much faster has got to be a good thing. And fortunately, some of this capability is provided now as well with Ignite through things like a normalization preprocessor. Okay, so let's just stop there a moment, and let me just stop this here for one moment and just quickly show you a couple of these algorithms which we talked about. Okay, so let me just minimize this for a moment. All right. Now, what I've got here is a download of Ignite from ignite.apache.org. So you can get the source, you can get the binary distribution. I happened to download the source a little while ago, and I built this locally. And as part of the examples that come with this, they've added these sort of machine learning under the Java directory here. So these are very helpfully divided up into a number of useful sort of categories, things like clustering, for example, k-nearest neighbor, for example. There's also code for matrix manipulation, and here we can see some examples here. So the nice thing about these examples is that they are standalone. So there is actually even no need to run an Ignite node to be able to do this. And let me just see what we can do here. So KNN classification example. Okay, so the benefit here is that with these code examples, because all of the Java code is provided for you, it's very easy just to be able to run this, and I can do this directly from the IDE. I can poke around, have a look at the code, see how it's designed, and there you can see most of these things run very fast. Now, they're working on sort of fairly small data sets, but again, there's nothing to stop you scaling this up and being able to try something on a much larger scale. And I'm actually in the process of preparing some blog posts and looking at some larger data sets to something that's a bit more practical and realistic.
Akmal, sorry, we lost you for 1 second or 3 seconds, just so you know.
Okay. Okay. Yeah. Are you okay there now, Rob? Can you hear me now? Okay.
We can hear you again. Folks, feel free to raise your hands if you have issues.
Okay. Yes. Yes. If anyone is unable to hear me, please let us know through the chat box. I apologize if the sound went down. Not sure what happened there, but I'm doing my best. Certainly, ensuring that I've got all the correct setup here. So using a fixed line rather than Wi-Fi and all the other things. But there we go. That's technology for you. So okay. One of the other things, for example, tracer example. So this is kind of matrix manipulation, right? And then this is all very simple stuff. So in this case, it does a little bit of matrix algebra, and so just happens to output onto the web browser in this case, and also on the console. So all of this code is provided as part of the distribution. Again, take your time. You can have a look at this sort of detailed algorithms that are provided. All the Java implementation code is there for you, and I'd encourage you to have a look at that. Okay, now I'm kind of conscious of time, so there's a little bit more to get through, and then let me just move on, because one of the things that was added to Ignite earlier this year was this donation of this genetic algorithms, what used to be called a genetic algorithm grid. Now it's just called genetic algorithms, okay? And this is a part of the machine learning library that's provided. You can have a look at this code today. Again, do exactly what I did. Just download the source from GitHub, for example. You can build it locally, but this will be included in the next official release of Ignite as well. So the code is already there if you want to have a look at it, or you can wait, which I think the next release should be out anytime. So this is great. So I was fairly new to this area, so I did a little bit of research myself to having a look at what this is all about. So it's interesting because it's an approach to solving complex problems using something that simulates biological evolution. So you have this notion of a population. Population consists of chromosomes. A chromosome is a possible solution, and then the chromosome itself consists of genes. And then you can combine these genes to derive new chromosomes. Okay, and there's a kind of a notion of mutations as well, and how to evaluate then when you get a good solution. So we'll look at that in just a moment. So with this genetic algorithms, then there's a couple of key things then. So this notion of fitness calculation, crossover, and mutation. So chromosomes contains a fitness score. Okay, this is a calculation that we make based on how close is it to the target that we're trying to match. And I again show you a little bit of an example of that working in a moment. Crossover, process of combining genes to produce new chromosomes. Okay, so again, simulating the process of human sort of biological, I said human biological evolution, not just human evolution. And mutation. Some genes within chromosomes are updated to produce new characteristics. So we change things a little bit to see what effect that has. And then once we do this, okay, the way this works, and I said before, remember, keep an eye on the sort of the graphic for the compute grid. You'll notice a very strong similarity between this and that. And so this works in a very similar way. So it takes advantage of some of the capabilities we talked about, such as collocated computation. But then how these are actually done in terms of fitness calculation, crossover, mutation, you can see it works in a very similar way using compute tasks that we had previously discussed about in the compute grid. In terms of the approach then, now I've talked about this sort of iterative nature of these machine learning algorithms, and here you can see a practical example of how this works. So after we've done our initialization, we do a calculation. Have we reached the termination point? Is the solution, do we have some results that we are happy with, or do we need to refine further and continue running this this task? And if not, then we can change it through selection, crossover, mutation, and then go back again and do this again. So here's a sort of practical example using the chart that I showed you a little while back in terms of the sort of iterative process that we use to continue to refine and look at the results and until we are happy. Okay, and let me show you this in practice. Okay, so this is a little bit more exciting and a little bit more interesting. So again, as part of the code distribution, this comes with, let me just close some of these windows, okay, and we'll have a look here. So this is the genetic. And obviously there's as we would expect, there is a hello world example, okay? And let me, just before running that, power up a node as well, because I want to show you something else in just a moment. So from the IDE itself, I'm just gonna start up an Ignite node, although I don't need to, okay? But we'll have a look at that in just a moment. And then something else, because I want to show you the web console as well. As part of that, I need to run this web agent as well, because I'm going to connect to console.gridgain.com. We can have a look at some sort of cluster information as well. So that's running fine. Now, with this genetic algorithm example, this hello world, what it's trying to achieve is that we have the string hello space world. And the words hello and world are all in uppercase. So that's the target that we're trying to achieve. And through the code, we're doing some mutation, we're doing evolution, okay? And the length of this is 11, okay? So that is the length of the chromosome that we've defined. Each of these characters represents a gene, and we're modifying each time. We're doing a comparison, and the exit condition, because we need an exit condition at some point, otherwise it would just keep going forever, is that once it's arrived at the solution that we're looking for, does it match the string hello space world? All of this code is provided here, okay? So the let me just scroll back up a little bit here. Okay, so the fitness function that determines and provides the score for each iteration, each chromosome, and then the terminate condition that we want to run. So let me just run this here, and this will run for a little while, okay? But let me just kick it off, and meantime, we'll have a look at something else. Okay, now lots of info messages here. It's just the logging that's going on to the terminal. Nothing to worry about. It's just the way that the code operates. So there we go. It's starting, okay, and what it's doing, it's just iterating different generations. As you can see, it's fairly early on in single numbers at the moment. Now this is going to take a little bit of time before it actually matches the solution. Meantime, let me just switch to the browser, and we can close this. And let me just go here. Okay, so this is the web console. So using this gives me the opportunity to have a look at what my cluster is doing and what sort of resources are being used. It tells me how many nodes. In this case, as you saw, I only sort of powered up one cluster node directly from the IDE, so there's not an awful lot of very useful information here. But if I scroll down, I've got a little bit of information here. It gives me some details about the caches that it actually has available. And one of these is called gene cache, which is something that the example code is actually using. If we switch back, let's have a look. It's still running. It's going to take, I think, a little bit more time to finish off. We're about roughly halfway through, having run this previously. Okay, I know this. That one of the other things that we can do from the web console is not just monitoring CPU, for example, looking at caches, but there's other things that we can change, memory policies, and so on. We have the ability to actually execute code as well. So SQL code can be run directly from the console itself. Now, in this case, this is again a standard capability provided by this particular library, the genetic algorithms code. It enables us to interrogate the gene cache, and there's a couple of functions that are provided as part of the code as well, which allows us to get some information about what's actually going on. And these can be done, as you can see, this is kind of standard SQL. We've specified the particular cache. Remember, cache is just an aggregate, similar to a sort of relational table. And then we can interrogate that by running this directly from the console here. Okay, now it might take a moment or two. There we go. All right. Okay. So this gives us a little bit of information in terms of the state of what's actually happening. So this very first row tells us the fitness score, and we can sort by this. We can see, for example, that this hasn't quite, none of these genes quite match yet. So let's switch back to the console. Okay, it's okay now. And so if I refresh this, Let me just execute this again now and have a look, see what we get. Okay, there we go. So this looks correct now. So the very first line, we can see that the it's 449 for chromosome. Fitness count was 11. Gene 1, 2, 3, 4, and 5 all match hello. 6 is the space, and then 7 to 11 match the phrase world. So this gives us a sort of an idea in terms of looking at how the generations of using this biological evolution to actually arrive at this particular solution. Okay. All right then. So again, I'm conscious of time, so we're almost out of time, and as usual, I talk too much. So just to summarize then, so key issues there to think about. So distributed machine learning and deep learning capabilities, things like TensorFlow, GPU support, these are on the roadmap. Okay, so I think watch this space. Should be very interesting over the next few months. Very useful again for the cases where when we can't fit that data onto a single server, when we need the capability of cluster computing, we need some of those advanced features such as parallelization, the ability to work across large data, the caching, and the benefits that Ignite provides in this space. It really goes far beyond what we can achieve just using a single machine. Zero ETO, very important again. So the ability to run and work upon the data that we have already in the cluster. And there is added sort of benefit as well, because if we're working with things like streaming technologies or IoT data, this is coming in, it's providing new data that we need to work on as well. So there may be historical data augmented by new data that's arriving, and our algorithms may adjust appropriately. But the fact that we can run this in place now, again, gives us a lot of benefits. Immensely scalable, okay? So we talk about horizontal scalability, obviously, because it's just adding new nodes as we need them. But of course, today, machines are very powerful. We can add more memory, add more sort of CPU power as well to machines, give us the horizontal scalability too, if we want. Memory is relatively cheap. Ignite provides the ability to store lots and lots of data on disk as well if we need that, far beyond what may be required just for in-memory. But again, it will treat the in-memory and the persistent data in the same way. And where data needs to be paged out, it will take care of that for us. So again, giving us the opportunity and the ability to work with really large amounts of data if we need to. This kind of partition data set gives us, based upon sort of MapReduce, gives us some fault tolerance and this continuous learning capability, which I kind of touched on a little bit earlier on, that we may not just be dealing with static data anymore. So as new data arrive, the algorithms need to take that into account. We're learning new things based upon this new information that we have available. So I think this approach is very, very important. It's kind of critical to a lot of the workings of these algorithms that we mentioned briefly. Okay, so I think we have a little bit of time for some questions. Rob, do we have any questions? Anything that, any particular issues that have been raised?
Yeah, we have a few. So first question was, where do you see machine learning starting to be used? How are people actually applying some of this?
Okay, so definitely, I mean, if we look at purely in terms of offerings, the literature, it's become far more prevalent today than it's ever been. When I started my IT career, I didn't know about this stuff. Nobody used it. I think today people are far more interested in using analytics, but just beyond analytics, the ability to try and get far more deeper insights into the data, looking for threats, opportunities, and again, we can see lots of applications. So some practical applications are in fraud detection, for example. So many of the large banks, this is a big problem for them, even today with all the security measures that they use. So I see there are lots of practical applications for machine learning. So in the fraud detection space, being able to pick up the fact that fraudulent activities are going on, very, very quickly, simply because we can run these algorithms very, very quickly. They will detect anomalies. They'll be able to detect things far faster than we would ever be able to do. And therefore, there's great applications for this just in that one space. So just in the finance space, I can see lots of potential. But across the wider sort of, lots of the other verticals that we briefly touched upon right at the beginning of the presentation that were on the architecture slide, I think there's a whole range of areas where really this is going to make some very valuable insights and inroads.
Great. We've been spending some time at IoT World in Santa Clara the last couple days. It's going on yesterday, today, and tomorrow. Wondering, for a lot of the discussions, it's actually been around predictive maintenance, finding leading indicators of issues. What typical types of algorithms would people use there?
Oh, good question. Can I take a rain check on that and investigate?
Yeah,
I will go and find out. That's a tough question. Thank you for asking.
Well,
whoever asked it.
I did it. I get no word for finally stumping you. I've seen linear regression. Yeah, okay. I've seen linear regression getting used just to try to find some correlation. I was curious if you're seeing things like genetic algorithms being used, neural nets, things like that.
Yeah, I think this whole genetic algorithms thing is very, very interesting. I mean, I'm new to this as well, so I was pleasantly surprised to look at this. Now, obviously, the example I showed today was fairly trivial. I mean, it's a very simple kind of problem. But one of the things that I've done a little bit of reading and research around this area, it's kind of a novel approach. And it takes a different way to kind of solve some types of complex problems. Now, it's not going to be suitable for all types of problems, and it's not, it will have its limitations, as all algorithms, as all technologies do to some extent. But it seems to me that this could provide a very valuable way, because if you think about biological evolution, then we introduce some changes, some mutations, okay? We change the data somehow. We're able to look at the next generation and so on. And the ability to evaluate these sort of solutions very quickly. Now, on my laptop, just that simple hello world, it ran for a couple of minutes, but because it was trying to evaluate different generations at each level, has it matched the solution that I'm looking for? So in this case, I know the answer I want to achieve, but what I'm trying to find is that, how good is the algorithm at being able to get to that answer? Now, there may be other types of problems where this type of things, I don't know, what answer I'm looking for. Perhaps I'm just looking to run this and then seeing where it takes me, what sort of insights can I get far beyond what I may be aware of. There may be sort of hidden data there or some useful relationships there, for example, and this could be a great way to do that. So I think there's great potential there. This is my understanding. And I think certainly it's very exciting time to have some of these things available through Ignite today already.
Great. Well, I think that's pretty much all the time we have, and those were some of the good questions. No other questions with which to stump you, so I apologize for that, Akmal.
Oh, okay, no worries.
I want to thank everyone for attending. I especially want to thank Akmal for presenting and going through this. Akmal, you have officially passed the Turing test.
Okay,
you are not a machine. So you're not a machine. So
yes.
Thank you, everyone. And we will actually be sending out, I think we'll be sending out slides later. We should have this up and available within a few days. So thank you very much, and looking forward to having you in the next webinar. I think we're going to be going through part one of a three-part series on it, really on best practices in memory computing, starting with adding speed and scale to existing applications. So with that, thank you all, and looking forward to seeing you again soon.
Yes, thank you, everyone. Thank you for joining.